If you have any questions at any point, please ask. So review of lecture 23, or more generally, the whole anomaly discussion. In our discussion of anomaly, we discussed two cases, chiral anomaly and scale anomaly. Chiral anomaly is an example of anomaly of gauge theories, which led to inconsistency of the theory. If you have anomaly cancellation, you could arrange for anomaly cancellation by arranging your field configuration, adjusting things, or like hand picking, making sure that the anomaly cancels. And scale invariance is we give it as an example of anomaly for global symmetry. This is scaling symmetry. This is not an anomalous theory, is anomalous scale invariance. Anomaly for scale invariance doesn't kill the theory. We interpreted this as beta functions for classically marginal couplers, right? So the theory is quantum mechanically fully healthy. For example, an example of this would be an important theory, QCD, or Yang-Mills. All right, good. So even though we said that chiral anomaly leads to an inconsistent nonsensical theory, we still said that mathematically there is a way of thinking about this as a set of path integral. And the way to think about it is that you could think of this anomalous chiral anomalous theory in two dimensions as the boundary of a gauge theory in 2+1 dimensions. So this is the boundary value of the fields on the 2+1 dimensional fields. And there is a contribution, there is an action you can write for the bulk gauge fields, 2+1 dimensional bulk gauge fields. So namely the Chern-Simons action. That's gauge invariant in the absence of a boundary. So the bulk theory is gauge invariant in the absence of a boundary. There's Chern-Simons term that's allowed. But the moment you introduce a boundary, it's no longer gauge invariant. There is a boundary term that spoils gauge invariance. And this boundary term is precisely calculating the chiral anomaly of the boundary 2+1 dimensional theory. Good. So this phenomenon is called anomaly inflow. I just wanted you guys to have seen this. So, yeah. In more advanced discussions of quantum field theory, it appears all over the place. And the connection between topology and anomaly is also here. We could explore more about it. Scale anomaly. So we discussed the scale anomaly in a simple setup of massless scalar fields. This theory is classically and quantum mechanically scale invariant. The conserved current associated to scale symmetry, the derivative of that, this conservation law, will give you tracelessness of stress tensor. Recall that we defined stress tensor using Noether current. Now, if we add to the action terms to form sum of I, GIOI, if the scaling dimension, the naive dimension counting dimension of G of I is not zero, they explicitly break the scaling symmetry. But if it's zero, these are classically marginal deformations which might not remain symmetries quantum mechanically. So these are naively marginal deformations or dimension counting marginal deformations. When you calculate beta of G at one loop, that's precisely the calculation of trace anomaly, right? Or the violation of scaling, conservation of scaling current at one loop, right? In principle, T mu mu has dimension D, space-time dimension. So all the operators that are exactly dimension D could appear on the right-hand side, right? The rule of thumb is that if there is no symmetry that forbids mixing between operators of the same dimension, they would mix, right? It's the same principle in renormalization group. If you don't have a symmetry that forbids the generation of certain operators, under the flow, they will get generated. They will be just generated. Good. So scale anomaly depends on the matter content. And it's possible to tune the content to get a conformal field theory, quantum conformal field theory, scale invariant conformal field theory, scale invariant field theory, right? Which is, if relativistic, we discussed this, right? Could become conformal. What are the generators of conformal symmetry? Plus. So it's Poincare. What else? Dilations. Special conformal transformations. But special conformal transformations could be thought of as in a simpler term. Is translation, inversion, inversion, translation, inversion, right? So you could think of it either as like special conformal transformations and dilations, or dilations and just one Z2 transformation, right? Inversion. All right. So today what we're going to discuss is a non-Lagrangian formulation of quantum field theory. Today in the next lecture. This is called operator product expansion or operator product expansion algebra. Algebra term here is a misnomer. There's no algebra. There's algebraic structure. What we'll cover today is not textbook material at all. But usually when people discuss operator product expansion approach to quantum field theory, it's discussed within the context of CFDs. But it generalizes to quantum field theory. It's just usually not it's not explained in textbook. So I decided to start with a formulation in quantum field theory. I'll go over it. And then next lecture, we're going to use this formulation for CFDs. But the formulation is fully general. And I'll try to make contact with the Lagrangian formulation as we go along. All right. So hopefully you should by now realize that like there is a departure from the whole framework up to here. Right. We're going to start talking about a different framework. I still formulate everything that in terms of things that look like Lagrangian field theory, but the principles would be independent. At any point, if things are vague or unclear, please ask. I realize that, yeah. All right. In quantum field theory, the fundamental object of interest are fields. In classical field theory, we assume fields to be smooth. They're C infinity functions of, say, R d comma 1. And the equation of motion for the field involve derivatives. That's good because the fields are smooth. They're C infinity, so we could evaluate derivatives. Even so, the equations of motions are PDEs, partial differential equations. Even Shockwave solutions, these are solutions with weak singularities, could still be treated within the framework of PDEs. They are singular, but they have a weak form of singularity, so you could still study. If this comment is technical, if you don't know what it means, ignore it. All right. Now, the discussion of the last lecture and what we saw in quantum field theory 1 was that every time you're dealing with fields, the natural thing to do, we don't have particles necessarily anymore. The natural thing to do is to organize your fields in terms of representation theory or background group, right? So for example, in the case of Poincare group, the representation theory in 4 dimensions was organized in terms of mass and spin. And those are the Casimirs, right? Those were the Casimirs that, yeah. In CFDs, the symmetry group is the Euclidean symmetry group, conformal group is SOD comma 1, right? This is in D space-time dimension, Euclidean space-time, right? Which happens to be the Lorentz group. Sorry, SOD plus 1 comma 1. This happens to be the Lorentz group in D plus 1 comma 1 space, right? So the representation theory is basically borrowed directly. All right. Let's talk a little bit more. So in the operator product expansion, or in quantum field theory, we take smooth functions, right? and map them to operators, right? A smooth function f becomes an operator phi of f, which is we usually think of in our heads as an integral of f of x against phi of x, right? That's what the operator is. And we often talk about phi of x as the kernel, as the operator value distribution, right? In operator product expansion, we focus on phi of x's as these operator value distributions. We focus on their singularities. So important. It's an operator value distribution and not an operator. Why? Because it has divergent fluctuations, right? What does it mean? It means that if an operator is well-defined, not only is expectation value is well-defined, but also its variance and all its fluctuations. What's the variance of an operator? The expectation value of A, operator A squared, minus the expectation value of A squared. Now, for that to be well-defined, phi of x squared as an operator should have finite expectation value. But that thing blows up. You know that it blows up, right? Because there are singularities that you calculate the two-point function, you take the limit of the 2 points becoming coincident, and it blows up, right? These were the UV divergences of quantum field theory. In operator product expansion, we mathematically, in a mathematically precise way, we deal with these fluctuations at small scales. We don't put the operators on top of each other, but we look at the limit, or not the limit, the small distance regime. Okay? So that's a basic concept. So we let go of F's, smooth functions. We talk about these operators as they become close to each other. Now, what does close mean in the Lorentz invariant theory? It means proper distance, right? It has to be covariant. So we're talking about proper distance. Now, as we bring two operators close to each other, they could be space-like separated and they're becoming close, or they could be time-like separated and they're becoming close, right? How do we distinguish between these in quantum field theory? I epsilon prescription, if you recall, right? This was precisely. This whole discussion goes back to the two-point function, right? I epsilon prescription was all about what, like we calculated, made sense of the commutator, right? We made sense of the two-point function, all of that using this I epsilon prescription, the contours, right? We took the two-point function, before we transformed it, we went to the complex plane, there were two poles, and based on we deformed the contour in various ways, going over both of them, going under the first one, and over, what do the two poles correspond to? What do they correspond to? Mass, plus minus mass, right? This is in what plane? P naught, omega, frequency plane, right? Going under minus m and over m in the contour in the Euclidean P naught corresponds to Feynman propagation. Going over both and under both, well, you remember what this was. All right, good. They're the advanced and retarded propagator. Good. Okay. Now, the basic idea is this. Consider for simplicity, free massless real scalar field in R3, 1, so that we don't need to introduce anything new fancy. The fundamental field is phi of x, right? We're going to look at the OP in the limit of epsilon going to 0 plus, right? This is to be treated as an operator statement. We say phi of x1, phi of x2 is 1 over 2 pi squared, 1 over x1 minus x2 squared plus I epsilon x1 0 minus x2 0. This is I epsilon prescription. Identity operator plus O of y plus other stuff. So what are we saying? We're saying that two operators near each other could be expanded in the basis of all composite operators, all operators in the theory. This is an operator statement. It's also an asymptotic statement. it's not operator statement. It's like, it doesn't literally hold because these are not operators, but it's an asymptotic statement, meaning that to make sense of this, you want to stick this inside expectation values. These are formal relations we could use inside expectation values, right? But expectation value of nice operator states, not every state. These kind of relations are called operator product expansion because we're taking the product of quote unquote operators, right? So what sits on this side is all the local operators. And so roughly speaking, you could think of it this way. Here's point x1, here's point x2, and the point y is anywhere in the middle, right? So what we do is we circle around this and we say the insertion of these two operators is equivalent to a sum over all 1 point insertions. So this is the main principle, but I'll go over it more and more so that it's clear. So you basically expand the insertion of two operators near each other in terms of all local fields in the theory. This is an asymptotic statement in the limit of x1 and x2 going to y. Are there any questions? Yes.
So just to clarify once. So the phi is considering an operator value distribution, right?
Yeah.
And in the operator product expansion, are those OYs operators or operator value distributions?
They are operator value distributions because they are defined at a point. Right? Now, these expectation values, these relations, to give you like expectation values, you have to insert them inside. So here is some sort of an expectation value in some state. I don't know. Psi. Now, if you have phi of x1, phi of x2, all sorts of other crap, you could replace this relation by a sum over p's of OP of y, a bunch of coefficients that are functions of x1 and x2 and y. CP. Yeah.
OP, y can be any operator insertion.
All the local operators in the theory. So what's the principle? To define a theory, you first have to define like your matter content, right? These are all the things that transform nicely. You know, there will be classified in terms of representation theory, the symmetry group, right? So all of them will be in here.
So this is like just Taylor expanding. Is you essentially?
It's more than Taylor expansion. It's more than Taylor expansion. Why is that? As you bring two, okay, very good. I'll actually give you, yeah, I'll tell you why. Like for example, just think about this. Remember normal ordering. Normal ordering in free field theory allows you to define phi squared. In renormalized perturbation theory, we define phi n. Right? Those guys are local operators. They are renormalized local operators. They appear here on the right-hand side. No Taylor expansion would give you such a thing. Right? Those are brand new novel operators. So I'll actually describe that. So these relations hold only inside as statements in the limit of x1 and x2 being very, very close to y, inside nice enough states, regular enough states. So this regular enough replaces the C infinity condition we've been talking about, right? For the fields, we're saying that for classical field theory, the functions have to be smooth enough, nice enough. What is the sense? How do I describe the class of states that I can use to stick these relations inside, right? So there's a class of states, there are a bunch of correlation. If I want to calculate the correlation function inside these states, I'm allowed to use these formal manipulations. The class of states is called Hadamard. This is a class of states. There are a class of states that are regular enough. All right. So here's the definition of Hadamard states. These are states that deep in the UV, they look like the vacuum of quantum field theory in RD, 1. Right? So what is the 2-point function of free scalar field in the vacuum in D, 1 dimensions? Sorry, in 4 dimensions, 3, 1 dimensions. What's the 2-point function if there are space-like separately? Sorry? Let's say the distance is much, much smaller than inverse mass. Deep in the UV, mass is a relevant deformation. Deep in the UV, the mass is irrelevant. So the 2-point function at very, very small distances. So very, very small distances. So you're right. If you have masses, it will look like e to minus mx something. But when you expand this, when x is very, very, mx is tiny, this is just 1, right? So this goes away. What does it look like? What's the UV fixed point? It's a parallel. The UV fixed point is? Yeah, just minus. So the theory is just minus del phi squared, right? So the 2-point function deep in the UV is fixed by dimension count. D minus 2. Right? So in 4 dimensions, this is just proper distance squared. The class of states that we're discussing, Hadamard, in arbitrary, they're just very formally defined. It could be arbitrary space-times, it could have curvature, it could be anything. They're defined using the following property, that when you look at the 2-point function of the fundamental fields, in the limit of these two guys approaching each other, is given by this x minus y squared, this thing, that has to be 1 over 2 pi squared. That's just proper thing for a Fourier transform. This thing is a function of x and y that in the limit of delta of x is 1. There could be a log term as well. Do you know why? Yeah, so think about in even dimensions, there could be a log term. What's the 2-point function in 1 plus 1 dimensions? It's log, right? In all even dimensions, there could be such a term. But this is also v of xx is 1. And then these are things that are just functions that in the limit of coincident points, these are finite. Sorry? Let me not try to explain that. Do I want to explain it or do I not want to explain it? Let me not explain it. Yeah, it could be there. Now, what does this mean? It says that, so these two terms capture the singular behavior of the 2-point function. The class of Hadamard states have the same singular structure as vacuum of flat space quantum fields. At long distances, it could be different, right? But deep in the UV, they look like flat space. That's expected, right? Good. This is what Hadamard states are. Every time you hear about them, notice that what is neat about this is that to define this class of states, I don't need to assume Poincare inverse. I don't need to assume anything. This is fully local. This is fully local analysis. All right. So these kind of formal relations in the limit of x1 and x2 going to y we're only allowed to use them inside correlation functions of Hadamard states. Any questions? Now, when you have these relations, What is nice is that because these are your fundamental fields, you can calculate all sorts of other things. For instance, you want to calculate del mu phi of x1, del nu of phi of x2, right? Well, that's easy to calculate. You had these relations for phi1 of x1, phi of x2. Just take derivative with respect to x1 of mu and x2 of mu. What does this give you? It tells you about the divergence structure of these 2 point del mu phi, del nu phi. Why is that important? Because it allows you, by subtracting the divergence terms, you define a finite operator. That's a composite operator. In the previous case, if I subtract from this limit of x1 going to x2, the divergent term, if I take this minus the right-hand side, this guy, or sorry, if I take this minus these two terms and take the limit of x going to y, that gives me a local operator. What's that local operator called? Phi squared. That's the very definition of a composite operator, phi squared. When I take del mu of phi x1, del nu of phi x2, subtract the divergence structure from it, take the limit of coincident points, it gives me a local operator that I can use to define which beast? Stress tensor. Right? Because stress tensor is half del mu of phi, del nu of phi, minus quarter or something, I don't remember, eta mu nu, del mu phi squared. This allows me to define renormalized stress tensor. That's good. What we're doing is actually a renormalization scheme. It's called point splitting renormalization scheme. So what we do is we define composite operators by subtracting all the UV structure. But the UV structure is dictated completely using the OP. Good? Any questions? This is a brand new formalism. I understand that it takes some time to digest, but this is really the modern way of thinking about quantum field theory. I'll go through this in more detail about conformal field theory, where we actually use this. Nothing about this is perturbative. What I'm telling you, even though I'm giving the example of free scalar fields, in full generality, this formulation is fully non-perturbative. Good? Any questions?
So, but this stress, the renormalized stress tensor is same as the normal order stress tensor.
And renormalized perturbation theory, yes. Meaning that if you did this for perturbative scalar field theory, yes, it's the same. Even though this might look different, but it's equivalent to that formulation precisely. With a lot of pain, people have proven these statements. All right. Okay, whoops. I did not write this down. Yeah, I think the order of my slides are messed up. This should be it. Whoops. This should be after this. Yep. All right. Now let's consider phi of x1 to phi of xn. Right? N operatorizations. I use the word operator, but you know it's distribution value operator. Operator value distribution. This will have an OP of this form. Sum over K of all the local operators in the theory, right? C of 1 to infinity of functions x1 to xn of y, this label K. These are called OP coefficients. And if I know this for phi 1 to phi xn, I can calculate everything for all these operators, phi k1, del k1, phi, I don't know, k tilde 1, phi kl, del K L phi K tilde L, right? I can calculate all of these guys. I can normalize them. I can consider composite operators, all of that. All that data is in this OP coefficients. So the definition of quantum field theory becomes a set of OP coefficients. These are functions of n plus 1 variables, x1 to xn, comma y. There is a label k that tells you, that labels all the local operators in your theory from 1 to n. Now, there are consistency relations that we're going to discuss now for these OP coefficients. Yeah.
So these OIs were non-composite operators. Well, yeah, they are non-composite.
Composite or non-composite.
Like, for example, I could just view each of them as non-composite. It would just be like ends. So on the right side, because you have 5 cases, so you need to say that in always expanding in terms of only non-composite.
You could say those words, yes. But the thing is, in Lagrangian formulation of quantum field theory, right, you have a list of non-composite operators and they're all related to phi's. But in a non-perturbative formulation, as we see for CFDs, you have a list of these guys, OKs, right? These are called conformal primaries. You just list them. So now, yeah, you could call them fundamental, and then you could talk about their composite things, but yeah. So in that sense, yes, these are, but yeah. All of these things, they have to satisfy all sorts of consistency relations, right? Well, we're going to discuss the consistency relations. Yeah.
One
No
totally different question. So, you mentioned that this whole formalism is totally non-particular. But then when I'm choosing Hadamard states, in some sense, I have to define it, how locally they are.
Yes, we'll get there. Yeah. When I define the Hadamard state, the Hadamard states I define basically give me perturbation theory around the trivial fixed point. Because I use the trivial fixed point for the 2-point function. I said the 2-point function goes to this 2-point function. That's quantum field to free scalar field. Now, as we'll discuss CFDs, non-perturbatively using operator product expansion, we'll discover more fancier theories where this is replaced by 2 delta, right? And then you will have another definition for Hadamard. So we will come from perturbation theory. Good. By the way, does this look familiar to you? Back in QFT1, we discussed a non-perturbative formulation of quantum field theory using path integrals. And we wrote a whole set of, what does this do for you? It relates higher point functions to lower point functions. When we discussed path integral approach to quantum field theory, the non-perturbative approach, we also wrote a set of equations that related higher point functions to lower point functions. Do you remember what they were called? Schrödinger Dyson. Of course, this is very much motivated by Schrödinger Dyson. Motivated, but not equivalent. In the OP approach to quantum field theory, we need a list of fundamental fields and their OPs. Here we go. We also have a dagger operation. So all these fundamental fields also will come with their daggers. There is another important notion that was just discussed, right? This thing. If you take the 2-point function, so take C I dagger I. 0 means the part of the OPE, so that means this. It means you're looking at O dagger of X, O of Y, 1 over X minus Y to a power of 2 delta identity plus da da da. Right? What is this? This is CI dagger I0. Oh, sorry. Right? This is C of I dagger. I, 0. That's the 0th operator. Right? X1, X2, and Y. So here I actually have X1 minus Y, X2 minus Y, but I can just take X2 to be equal to Y to get this form. Scaling degree of this beast is just delta. This is called D of I. That's the scaling dimension of the operator. So in my definition of Hadamard, I was assuming that the fundamental field, which was the scalar, real scalar field, had scaling dimension, scaling degree, D minus 2 over 2. Right? But in general, this could be more general. And the scaling degree is encoded inside these OP coefficients. So OP coefficients know about. To call them coefficients is a misnomer. These are OP data, perhaps because they're functions. In CFTs, we separate the functionality of it, and then we talk about OP coefficients. Is this concept clear? We'll get used to it a little bit more. Now we have to talk about the axioms of quantum field theory. First thing, these OP coefficients, these C of x1 to xn, of k, I1 to in, and y, they depend locally and covariantly on the background space-time points. Right? The OP coefficients satisfy appropriate anti or symmetric or anti-symmetric properties of the fields, where OIs are space-like separated. Make sense? Why? Because OIs come in representation theory of Poincare group, representation theory of Poincare group, including projective representations. That includes spinors, which means that whatever function we put, if they are bosons, it should be symmetric. If they are fermions, because of the spin statistics theorem that relates the statistics to spin, right? It will have to be antisymmetric. So the half integer representation spins are antisymmetric, the integer ones are symmetric. When they're space-like separated, of course, right?
So wouldn't we say that we are only looking at states which locally, I mean, we are in that regime where the background is, sorry, those states which don't have any localized kind of excitation. As in locally, background is flat. So
yeah.
Then how would OPs know about the global backend junction? The last one you mentioned.
Oh no, this just means that if you, so for example, these are, if you put x up, let's say x up, here's x and y, right? There is local action upon Poincare group. So it's flat space locally, but there's still Poincare group acting locally, right? So for example, this you could translate both of them at the same time. You could boost one of them, or boost them around different points. Locally, they should act covariantly.
Yeah.
This need not be global.
Yeah, but they cannot. So that last word which you written on the background space line, they don't really know about background space. It's just background.
Depends. So I haven't told you their radius of convergence of these relations, right? So yes, if you have curvature, actually, if you have curvature, these OP coefficients, the curvature will be encoded inside these OPE functions, right? So they know about the curvature of space, but this is too advanced for this class, right? For example, if you try to formulate free fields, non-interacting free fields in curved space-time, you precisely see what happens over there. So only these, so your starting point is the OPE of flat space. and then you see how the curvature will enter the OP functions. Now, there's a funky one. This Cj 1 to n, this OP of endpoint functions, should be bounded in terms of d1 and dn of the fields. Does this make sense to you guys? What does it mean? Can you give me an interpretation for this? What was the interpretation of di? It's the scaling dimension of the operator, right? Now you're bringing in n operators of scaling dimension, d1, d2, d3, d4. If the theory is completely free and these guys just add up in a nice way, what's going to happen is that the object, it is completely non-interacting, is going to have the scaling dimension d1 plus d2 plus d3 all the way to dn, right? If we recall phi n that we defined, the composite operator we defined phi n, when all the interactions were absent, just had dimension phi times n, right? It was n times d minus 2 over 2. Now we had anomalous dimensions that told us in perturbation theory, there could be anomalous dimensions. This says that the anomalous dimensions should be finite. It should be bounded in terms of d1 to dn. It shouldn't be possible that you bring in n operators of fixed dimension and get something with arbitrary large dimension, right? Anomalous dimension need to be bound. Not very difficult, but an interesting condition is this: C0 O dagger O has to be positive. You guys know why? It's a fancy one. It requires some deeper understanding of quantum field theory. Let's not worry about it. I just want to go down. There are two more conditions that I want to go over. Any questions so far?
Is something to do with positivity of energy?
Mm-hmm. Well, in flat space, yes. In more generally, it has to do with the construction of the Hilbert space, the positivity of norm of the states. If you want to know why, well, remember free field theory, right? What did we have? We had the Poincare invariant vacuum. Phi of x acting on this created x1, created a one particle excitation on top of this, right? Now, if I want to calculate the norm of this, the norm of this better be positive. What does it look like? It looks like phi dagger phi at some point insertion. It's a two-point function, right? If you look at the requirement that this two-point function, the norm of this guy is positive, it translates to positivity of C0 phi dagger phi for all phi's. So it has to do with the positivity of norm, right? There are two more conditions that I want to go through. These are fancy conditions, but I'll promise 10, 15 years from now, the textbooks would be discussing these in detail. We never learned about this stuff when we took quantum field theory. It's none of the books because the books are outdated. Spectrum condition or positivity of energy. This is the statement that the theory should be stable, meaning that take any vector in the Hilbert space, any state, the expectation value of P mu better be a future directed time-like vector or not. Now, I leave it for you guys to argue because based on everything you know, even QFT1, you could argue for these. This property holds if phi x acting on the vacuum gives you a combination of one particle states with time-like or null momenta. That also translates to the following statement. The two-point function in momentum space looks like theta of k1 0, delta of k1 squared, Dirac delta function of k1 plus k2. This says that the two-point function of k1, k2 has to do with the contraction of a future directed null momentum. This is future directed. This is null momentum. And it has to be contracted with a past directed null momentum. This translates to this, ensures this. It's very simple to argue, but I absolutely recommend. It just, this follows from like canonical quantization. Like it's very, very simple, but it's important to think about it deeply, why it holds, because in our modern way of understanding quantum field theory, this kind of structure is generalized beyond the standard canonical quantization, where canonical quantization we don't know how to do properly. So there is one issue. In a general, so here, this slide is very, very advanced. I understand that, but I want you guys to have heard this. In a general space-time, there is no Fourier transform or preferred vacuum. There is a notion of wavefront set, and the analog of this relation, right? The positivity of the theory, an analog of these relations, they're called the micro-local spectrum condition. They are a set of conditions that C0, phi, x1, x2. Hopefully it's clear. And they have to do with, as you bring x1 and x2 very, very close to each other, it basically looks like flat space. So on the tangent bundle, which is flat space, you have Fourier transform. You could do Fourier transform. That's called front wave, blah, blah, blah. There could be singularities in the other direction, blah, blah, blah. All of that aside, what matters is that you mimic as closely as possible this structure in the limit that two operators are coming close to each other. All these fancy words is functional analysis for the simple concept that locally, as you bring the operators close to each other, this is the structure you should expect. Interestingly, this condition, spectrum condition, combined with positivity of C0 phi diagonal phi, with the spectrum condition, together they imply the Hadamard condition, that the state is Hadamard. So they're related. These relations are all related. Okay, so what did we say? One of the most important axioms in the operator product expansion formulation is an analog of positivity of energy. You might not have a notion of energy. For example, in Kerr spacetime, you don't, because you don't have Poincare group. But you still can abstract out some notion that's local, and it comes out of the behavior of the two-point function as you bring them very, very close to each other. And it mimics or generalizes positivity of energy. Good? There is one other condition. This is perhaps the craziest one. Well, I can't say most important, but it's a very, very important one. Operator product expansion is associative, should be associative. What does it mean? So how are we going to use operator product expansion? Let's say you have a three-point function in some state psi, which is Hadamard, so we're allowed to use O1, O of x1, O of x2, O of x3. You could write down directly the OP of three operators, right? In terms of, say, 1, 2, 3. O1, 2, 3, K, x1, x2, x3, y, k, O, k, y. Or you could do this. You could write down the OP of these two guys. Then Write down now the OP of these two guys gives you a sum over one operators, single operators. Then apply the OP of these two guys. That's like multiple, like there's no multiplication, but OP of these two, then this, or you could do these two and then this. The fact that these two orders, procedures should match, it's called associativity. People have been trying to solve associativity conditions and they've used them to find or like restrict the space of non-perturbative quantum field theories, where we don't even know about action principle or anything like that. This is, if you've ever heard of conformal bootstrap, this is precisely the program that they try to write down the associativity condition for operator power expansion and use them to restrict the space of non-perturbative quantum field theory, conformal field theories. Right? So if you take these two guys, you first expand in this channel, it's called. This is what you get, and then expand in the result with this guy. Or if you do 2, 3, and then expand it with this, the results should match. Good? Okay, I'm running really behind. Now, there's also an interesting other property. We had renormalization group. Can we form a renormalization group here? Yes. Right? You have the 2-point function for some value. The simplest case I can think of is m squared. Del m squared of the 2-point function. You could just use the Schrodinger Dyson equations that you do know to write it this way. It's basically the propagator from x1 to x2 is like propagator from x1 to y and y to x2 integrated over all possible locations of y in space-time. Right? In lambda phi 4, this is literally an equation we had on our slides in QFT 1. Del lambda of G2 x1 x2 for lambda equals 0 has this expression. More generally, the endpoint functions could be written using the propagator and, m plus 1 point function could be written as a propagator and lower point functions. Right? Or connecting lower point and higher point functions. We had this infinite set of related correlation functions. These were called the Schrodinger Dyson equations. You could easily convince yourself these are analogous to flow equations for the OPEs. So del lambda of C1 to N of J of X1 to Xn of Z will have to satisfy these OP relations. I'm not going to worry with the details of this. But turns out you could solve these relations as formal power series as lambda. All you're doing is that you're formulating perturbative quantum field theory using the operator product expansion. This is equivalent. What is neat is that if the lambda equals 0 fixed point satisfies associativity, these relations guarantee that they will remain associative at finite lambda all along the flow. So quantum field theory will just continue to hold, all the axioms continue to hold. This formulation does not require Lagrangians at all. Nowhere in this we use Lagrangians. So in the derivation of Schrodinger Dyson, you might say, oh, you use these path integrals and attractive theories. Are they really finite? How do you regulate them? All sorts of song and dance, right? Here, you just don't care about any of those. Inspired by Schrodinger Dyson equations, you define these OPEs, and you hypothesize or say that you require that they satisfy these equations, right? That goes into requirements for the existence of quantum field theory. Now, perturbative quantum field theory or non-perturbative CFTs we found, we can check they satisfy all of these relations. Now, the question is, are there other theories we can discover for which we don't have any Lagrangian formulation. Well, examples of that would be 2D CFTs. 2D CFTs satisfy these equations. Some 2D CFTs that we don't have Lagrangian formulation for. All right. So in summary, up to here, I walked you through another approach to quantum field theory, which was based on operator product expansion. We let go of those smooth functions. We talk about smooth functions were replaced by regular enough states. Regular enough means that the 2-point functions look like flat space vacuum. These are called Hadamard states. And then we had these formal relations. We call them operator product expansion. And the data of quantum field theory are these OPE data, right? And they had to satisfy a whole list of criteria. And there were some positivity relations, but an important one was associativity. We can make sense of a normalization group for them. We can use them to define composite operators. All the success of renormalized perturbation theory is just mapped to these as well. You could do that here. This was done very painful work in the past couple of years. Good. Now, this stuff you can't really find in textbooks, but I wanted to tell you that this story so that to kill any doubts that operator product expansion applies to quantum fields. Now, it turns out that it's a lot more helpful, useful in conformal field theory. To classify conformal field theory, because the theories has so much symmetry that we could actually use these associativity relations to actually sort of limit the space of possibilities. But they formally hold for quantum field theory as well. It's just so far it has been beyond what we can explore. There are some, like past couple of years, there have been a couple of papers on this. People are trying to explore this, but it's really unexplored territory. Good? Any questions? Yeah.
You said like there's some ones where we don't have a Lagrangian formulation. Is
Correct.
that like we know there isn't a Lagrangian formulation, or we just haven't found one?
So you see, there is. To say that there is no Lagrangian formulation is a very, very strong statement, right? Because we allow, as you see it in the case of gauge theories, we allow all sorts of Dirac delta function or constraints inside the path. There are theories that we know that they exist, that we know there is no way of writing them as path integrals without constraints. There are many examples of those, right? But it's just hard to prove there is no way to formulate the theory that way. But the point is, if you just get really focused on Lagrangian formulation, it's extremely hard to guess the existence of such theories. A very good example of that, actually, think about, this is a real beautiful example. Let me see how to say this. Think about free scalar field in free scalar field theory, yes, in 6 dimensions, 5 plus 1. Start with the Lagrangian, which is just free theory, del mu 5 plus m squared phi squared. Try to add a term to this. That is even like marginal or relevant, right? Any operator you write down is going to be irrelevant. So the existence of genuinely interacting 6-dimensional quantum field theory is a puzzle from the point of view of action terms, Lagrangians. But we do know they exist. There are CFDs. There is like a very famous theory that appears from string compact deviations. We know that they exist. We have all sorts of properties. We know all about them. We know a lot of their properties, but they're just wild to write down an action for them. Just because of the fact that, like, yeah, you want to write down something that it looks like marginal, and maybe quantum effects will make it relevant. If you write down something that's like irrelevant classically, that's pretty bad, right? Okay. So now in the remainder of this lecture, whatever is left of our time, and the next lecture, we're going to focus on operator product expansion as a formulation, as a non-perturbative, non-Lagrangian formulation of conformal field theory. So when I was learning quantum field theory, my biggest question was that we learned Peskin-Schroeder. It's all about Lagrangians. Then you want to learn about conformal field theory. They say all that Lagrangian stuff, forget about it. Now we're going to talk about something else. I wanted to squeeze this lecture in the middle to just tell you that all that we discussed, this OP we discussed in studying CFDs also applies in quantum field theory. It's just very hard. And it's equivalent to everything you've learned. Even goes beyond that. Now, what is a conformal transformation? This is important. It's a diffeomorphism that multiplies the metric by an overall function. That's the very definition of a conformal transformation. It must be a diffeomorphism. Example, Poincare group for flat space. These are special diffeomorphisms. They're called isometries because they preserve the metric. Conformal transformations, the ones that transform the metric this way, they preserve the angles. You know why? Think about it. Why do they preserve the angles? Under an infinitesimal diffeo, x mu goes to x mu plus epsilon mu of x. You could also convince yourself g mu nu goes to g mu nu minus del mu of epsilon mu plus del mu of epsilon mu. What is this actually? How do you calculate this? Yeah. So metric is a 0-2 tensor. So under a diffeomorphism, it will transform as del x prime mu, del x alpha, del x prime mu, del x beta. You expand these guys to the first order, epsilon, and that for your diffs, right? And this is what you get. This has a name. It's called the Lie derivative of a metric. All right. So a conformal transformation will have to satisfy the following property. The infinitesimal conformal transformation will have to satisfy, it has to shift the metric by function multiply the metric. This function, by the way, is the log of the previous thing, log of this guy. Right? All right. So this is a relation that must hold for infinitesimal conformal transformation. Take the trace of both sides. You're going to get f of x is 2 over d del mu epsilon mu. This is, I'm assuming it's Euclidean, right? For simplicity, I'm going to focus on the Euclidean proof. Take this relation, take derivative with respect to del rho. You're going to get these relations. Contract with g mu nu. Contract with g, and you're going to get this relation. Finally, take this guy, take derivative with respect to del mu, and you're going to get these relations. Contract with, oh my God, I keep switching, g mu nu, and you're going to get this relation. So here are the 3 relations you need to keep in mind. They all follow from this. 1, 2, 3, 4. These are the relations. They all follow from this, right? I take just various traces or derivatives of both sides. Now, let's start simple. At d equal 1, any function can appear on the right-hand side of conformal transformation. Do you know why? Well, it's just because there are no angles. In d larger equal to 3 dimensions, this is non-zero. Therefore, f should have del squared of f has to be 0. It has to be a harmonic function. That tells you that f of x has to be a plus b mu x mu. So that solves this equation. then you plug that back in inside these relations. You just solve it. I trust you guys can solve it. You find that these are all the conformal transformations that exist in 3 and higher dimensions. Whoops, I think this is wrong. Now it's correct. No, still more. Oh, x mu. Yeah. Lambda x mu. Oh, God. Yep. These are all the relations. There are translations, dilatations, rotations. This is the Euclidean Poincare group, which is SOD. Then we have the special conformal dilatation is not on there. So translation, yeah, anyway, translation. No, I misspoke, sorry. So you have translations, dilations, rotations, and special conformal transformations. Special conformal transformations could be written in this form, which means inversion, translation, inversion back. This is inversion. Solving all of this together, you learn that lambda of x is parameterized by a vector called b mu. This way. This is lambda. Lambda of x. Good? Okay. So this is the end of this lecture. What did we do? We formulated operator product expansion. We discussed operator product expansion as a different non-Lagrangian, potentially non-Lagrangian formulation of quantum field theory. We focus on associativity, right? And now we're talking about conformal transformations. Why we're doing this is that we want to label or organize our representation theory because we want to organize all our local fields. Once we have all our local fields, all that remains is that I have to think about bringing 2 of these local fields nearby and expand the result in terms of local fields. There will be OP coefficients, right? That's all I have to deal with. And I have to use the conformal symmetry to simplify this algebra and these associativity relations, right? This is the route to non-perturbative understanding of CFTs. All right. Any questions? By the way, here what I discussed was I discussed the conformal transformations in D equals 3 dimensions and higher. This is the full group. D equal 2 is special. You know what's special about this? So this analysis that I did applies in D equal 2 as well, but there are other generators. It's actually infinite. There's an infinite number of generators. So we'll discuss that next time. That's the reason that 2-dimensional CFDs, we know way more about them because the conformal group is very, very large. It's called the Virasoro. It's the WIT algebra. WITT algebra is infinite dimensional. All right, any questions? Can you say it louder?
Like the 5th dimensional category, like the 5th axis.
Yes.
About the direction, like the expectation of the being.
Right.
So you mentioned that somehow this related to positive
Energy. Yes.
But I thought there were no local positive because the matrix that we get.
There are say again.
There are local positive.
P mu is a global operator, right? That exists in a theory that's translational invariant.
Yeah, but like I could choose states which have settled only in, but I guess they won't be.
Say it again.
Can I like choose psi to be state which has a local symbol.
Sure. So the thing is, here's the thing. There are no local energy conditions. Well, there are no naive local energy conditions in quantum field theory. The local energy density could be arbitrarily small. But these relations still hold, meaning that if you have negative energy density at the point, somewhere in space-time, you're going to pay penalty for it. Yeah. This P mu is a global operator.
Oh, it's not the density, it's the.
No, this is the generator of, this is momentum.
So this is the average.
No, average inner conditions are different. This is P mu. Average inner conditions usually, so this P mu is supported on a codimension 1 surface, right? Average inner conditions are often supported on a world line. So they would be the same in 1+1 dimensions, but in higher dimensions, it would be different. Any other questions? How many of you guys had seen Aubrey Park's match? Oh, no, yeah. It is really becoming more and more the dominant way we think about quantum field theory. So you will see more of it. All right. Any last questions?
No question.
Do we require the setup local for